In this video, we're going to look at the differentiation rules. In a previous video, we saw how to take derivatives using the formal definition of a derivative, that is the limit of the difference quotient. But that is cumbersome and that is a long process, and there are some shortcuts we can take. Now, it is important to recognize that these shortcuts, these rules, are not the definition of a derivative. They are results of that definition. So we cannot get to any of these rules without that formal definition of a derivative. That's why we started there, and that is why it's still important to know. Now, in this video, we're going to cover some of the basic rules. There are additional rules, and they're just things that we don't have a rule for, and so then we have to go back to that formal definition. So, first off, let's define c and n to be any real numbers, f of x, g of x to be any differentiable functions. Then we get the following rules. First rule we have is constant rule, and I should note too that I'm not going to prove any of the rules we see today. I'm just going to do examples of these rules. All the proofs can be found in the book, and you can find videos for how to do those as well. They're not real difficult, especially some of these earlier ones. The sum and difference, pretty easy. The product quotient rule, they are a little bit more challenging. Really not too challenging until we get to the chain rule, which will be a later video. So the constant rule says the derivative of constant is equal to 0, and this should be pretty easy because we know that a derivative is just a rate of change, and so as a rate of change of a constant, it's just 0. The power rule, we've seen this already, we haven't seen the formal proof of it, but we've seen how it seems like exponents tend to step down by 1. We took the derivative of a quadratic function we saw as linear, we took the derivative of a linear function we saw as just constant. So this shouldn't be real surprising, but if we take the derivative of x to the n, we can bring that n to the front, the exponent to the front, multiply that to the x, and reduce that exponent by 1. The constant multiple rule. If we have a constant multiplied by a function, we can take the derivative of that function and simply multiply it back by the constant. The sum rule. If we're adding two functions together, and remember these functions have to be differentiable, if we're adding these functions together and we take their derivative, we can take the derivative both separately and just add those two things, or we can take the f prime plus g prime. The difference rule. If we have the derivative of two functions being subtracted from one another, we can simply find the derivative of each function separately and then subtract. Product rule. This is where it gets a little bit more challenging. We have two functions being multiplied to one another and we want to find their derivative. We have to leave the first function, multiply it by the derivative of the second, and then we leave the second function and we multiply it by the derivative of the first, and we add those two things. So leave the first, multiply by the derivative of the second, and then add the second times the derivative of the first. Quotient rule, also a little bit more challenging. So if we have f of x divided by g of x, we leave the bottom function, we multiply it by the derivative of the top, minus the top left alone times the derivative of the bottom, over the bottom function squared. Now this one does have the caveat that g of x can't be equal to 0. The function can't be equal to 0 because if it is, we obviously have undefined quotient. And then finally, the derivative of the natural exponential function. This isn't a rule as much as just a fact of life. The derivative of e to the x is just e to the x. And so we're going to be using this throughout, and we're going to use this later on to help us find the derivative of other exponential functions, not just the natural. But that will be a later video as well. So this e to the x function, we've seen in the past, we saw in pre-calculus, it's a very special function. We know that it kind of tends to be the base of how things grow exponentially. Populations or money, we saw in the compounded continuously growth rate. But more importantly, the reason this function is so important, so unique, it perfectly models its own rate of change. Remember, derivative is just rate of change. So if we're taking the derivative function and it's equal to itself, that means this function models its own rate of change, and that's why it tends to be such a special, interesting function. So we're going to do lots of examples, and I'm going to start off very simple. So let's take the derivative of 5x. Well, what I see here is I have a constant 5, so now I can just bring that 5 right over and multiply it by whatever the derivative of this other half of the function is. So I have the derivative of x. Well, if we think about x, the exponent on that is just 1. So I'm going to write this first one out very formally. I won't do this from here on out, but I take this 5, I'm going to multiply it by the 1. And then I have the x still sitting there, but then I have to take that exponent and subtract it by 1, so I'll have 1 minus 1, which is 0. And of course, anything to the 0 power is just 1. So I have 5 times 1 times 1, which is 5. So the derivative of 5x, x being just to the first power, don't need to write it, is just 5. Let's take derivative of another one. Let's take 3x squared minus 2. Well, in the first one we used constant multiple rule and we also used a power rule, so we kind of combined multiple rules there. We're going to have to do the same thing here. We have yet another rule. We have a difference here, so subtraction, so we're going to have to use our difference rule, and we also have a constant multiple, so we'll have to bring all these rules into play. So here we have 3x squared. I'm going to do this one a little bit faster than I did above. Rather than writing it out, I'm going to take the 2 and multiply it directly in front. 2 times 3 is 6. And then I'm going to take that exponent and reduce it by 1. So it was x squared, now it's just going to be x to the first, or x. And then the derivative of a constant is just 0, so we're left with the derivative 6x. Let's take the derivative of 5x to the 9 halves minus the 3x squared plus 2x. So now we've included even more rules, and we're going to have to think about all those rules. So we have some power rules, we have some constant multiples, we have a difference, we have a sum as well. So we're going to have several rules here to deal with. So now I take this exponent and multiply it to the front. 9 halves times 5 is 45 halves. My exponent was 9 halves. I know I can just subtract by 1. It doesn't have to be a nice pretty whole number. It can be any fraction. So 9 halves minus 1. Well, I have to have a common denominator there, which would be 2. So 9 halves minus 2 halves will be 7 halves. Then I move on to my next term, and it was subtraction, so I'm going to leave it as subtraction. I'm going to multiply that 2 to the front. 3 times 2, we saw this just a second ago, it was 6. And then we reduce that exponent by 1, and now it's just 6x. And then we have the derivative of our last term. It was being added, so I'm going to leave it as addition. And the derivative of 2x, kind of like what we saw in that first one, it's just going to be the coefficient, because we multiply the 1 to the front. 1 times 2 is 2, and then x 1 to the first minus 1 is x to the 0, which is just 1. So we're left with just a 2 in the back there. And so this would be our derivative. Let's make them a little bit more challenging. So let's take the derivative of the 5th root of x minus 3x to the 5/7 plus the 8th root of x cubed. I'm going to write this one underneath just so I have a little bit more space to do my work rather than just writing it to the side. It's not quite as easy this time. So we're going to take the derivative of each of these terms first, but we didn't talk about radicals. We don't have a radical rule, but remember, radicals are just fractional exponents. So if I wanted to, I can write this x, the 5th root of x as x to the 1/5. Now that next term was already perfectly set up to be able to take the derivative. It already has a nice fractional exponent, but then again here in the back we have a 8th root. I want to write that as an exponent. Because x was raised to the 3rd power, that 3's got to stay in the numerator, but the root always goes to the denominator, so it'd be x to the 3/8. Now notice a little bit different on this one. Every problem up to this point, I've just dropped that d dx in the front. I've dropped that differentiation operator. I've dropped the d dx because I've just found the derivative in one step. Here, in order to find the derivative, I've had to do a little bit of work first. I've had to rewrite these in a slightly different expression. So for that reason, I haven't found a derivative. I couldn't just say that this is equal to this expression. That would be false because I haven't taken the derivative yet. So I've got to keep that d dx operator in front. Now I'm actually going to find the derivative. So I'm going to drop this d dx. So I'm going to multiply the 1/5 to the front. The x is now to the negative 4/5. So we can have negative powers, that's fine. We took 1/5 and we subtracted 1, 1 being 5/5. We got negative 4/5. Then I have minus 3, and I have to multiply that by the sevenths, so 3 times 5 sevenths is 15 sevenths. X to the now negative 2 sevenths, because we have to subtract that 5 sevenths by the 1, so that gives us negative 2 sevenths. And then we're going to have plus 3/8 x to the 3/8 minus 1 would be negative 5/8. So these things continue to work even if we have negative exponents. We can deal with negative exponents, that's not a problem. Notice I did drop the d dx on that last line. And notice one other thing too, I see this happen a lot, and really it's bad practice. I don't want to take the derivative of this middle term right away. I know it's already set up to very easily get to that negative 15 sevenths. We could have done that in the very first line. But I don't want to go taking the derivative of half the problem without doing the whole problem. So I want to get the whole problem into a setup that I can take the derivative of very easily. I want to do it all in one step. Let's do one more example before we move on to the product and quotient rules. I just want to show you that we can work with even negative exponents. So let's say we had x to the negative 7 minus 2/3 x to the negative 5 halves plus 2. Now I take the derivative of this. So it's in a format very easy to take the derivative of right away. So the negative 7, that multiplies to the front. And then I subtract negative 7 by 1, it becomes negative 8. Remember, those numbers are going to get even larger in the negative direction when we are subtracting a negative by 1. Negative 2/3 times negative 5 halves, well, the 2's will cancel, and so we'll be left with a positive 5/3. We subtract that exponent by 1, so negative 5 halves minus 1 would be negative 7 halves. We have to subtract by 2 over 2. And then the derivative of 2 is just 0, it's a constant, so that would be our answer. Right, so that was a lot of examples looking at the sum, difference, power rules, the constant multiple rules. We're not going to forget those, we're still going to use those, but I want to bring into the product rule as well. So let's take an example. Let's say we want to find the derivative of 3x e to the x. Well, 3x isn't just a constant multiple. The 3 is. 3 is a constant multiple, so we can just pull that out front and leave it for later if we want. But the x is not a constant multiple. E to the x is not a constant multiple, so now I have two terms. So what I'm going to do is mentally break these up into two factors. What I'm going to do is mentally break these up into two different factors. I'm going to view them very directly. So what I'm going to do is I'm going to group these first two factors together, 3x. And like I said, I can pull the 3 all the way to the front if I want to. It's just not real hard to work with on the x. That means e to the x is my second grouping. So what I've done is I've created two different factors here in order to be able to apply my product rule. I'm treating it almost like, well, I'm treating it like two different functions. So my product rule says, can leave the first function, the 3x. We can take the derivative of the second, e to the x. Well, that's very easy. It's just e to the x. And then I'm going to add to that, I'm going to leave the second function, and I'm going to take the derivative of the first function. Derivative of 3x is just 3. Then, of course, it looks a little funny to write the 3 in the back, so usually I'll just pull my constant multiples to the front, or I do it in my head at the same time when I was doing the derivative. But this would be my answer. So again, what we do is we have to view it in terms of two different factors. Take the derivative first, we leave the second, and then we take, excuse me, let me try that again. We leave the first, we take the derivative of the second, and then we leave the second, we take the derivative of the first. Now, actually, it doesn't matter. I started to get it backwards there because as long as we do the derivative of one, leave the other, and then do the derivative of the other, leave the first, it doesn't matter the order because addition is commutative. Now, that's going to be a little bit more important that we get the order right when we get to the quotient rule because we had subtraction in between. But with multiplication, you'll see me kind of do it both ways just depending on how I feel. Sometimes I'll do the derivative of the first to leave the second, and then I'll do the derivative of the second, leave the first. So it really doesn't matter a ton there. Let's take another example. This time I'm going to take the derivative of 1 over x cubed, x to the 5th minus 3x to the 4th. Now, there might be something obvious jumping out at you that we could do that make this problem a lot easier, but I'm going to kind of ignore that for a second. I see a product here. I see one factor, I see a second factor. So I'm going to use my product rule. Like I said, I'm skipping the obvious, the easy thing to do, but we'll do the obvious easy thing in just a second. Now, one thing that's a little different, 1 over x cubed, I've not seen that before. That's a little different. So I need to view that in terms of just an x to a power. And remember, I can always rewrite fractions as the reciprocals with negative exponents. I can write that as x to the negative 3. And that fixes that problem. Now I have an x to an exponent that I can just apply a power rule to. So now we'll actually apply the derivative. Notice I left the d over dx in front because I hadn't done the derivative yet. I just rewrote the original function. Now I'm going to take the derivative of this expression. So I have one function times another. So we're told to leave the first, take the derivative of the second. Now if I'm going to take the derivative of the second, now I have to use a product rule and, a power rule and a difference rule within that product rule. So power rule says I'm going to multiply the 5 to the front. The exponent goes down by 1. And then here I have a constant multiple rule, so I multiply the 3 and the 4 and get negative 12. Exponent goes down by 1. I'm going to add to that. I've got to this time leave the second and then take the derivative of the first. And the derivative of the first will be a negative 3x now to the negative 4. And now we do have a derivative, but it's not in any way simplified. So I'm going to go ahead and simplify at this point by distributing. So I have x to the negative 3 times x to the negative 4, give me just an x. And then x to the negative 3 times x to the 3 will cancel, just give me the 12. So those come from the first two terms. Then we're going to take this negative 3x to the negative 4 and distribute it to both of our terms here. So we'd have a negative 3. Let me get rid of that plus and switch it to a negative. So minus 3x, and then we'd have the negative 3 times the negative 3 giving me a plus 9, and x to the negative 4 times x to the 4th, those will cancel, just give me the 1, just leaving me a 9. And then simplifying finally, I can add my like terms, so 5x minus 3x will be 2x, negative 12 plus 9 will be negative 3. And that is my derivative. But I said we missed something very obvious in that very first step. We didn't have to treat it like a product because just like we saw here, these are like expressions. We can multiply them out and simplify. I could have multiplied these things together too. So that would have been by far easier. Let's just see what we get when we do that. I'll do it in blue just to see if we do get the same answer. So dx of x squared minus 3x, now just to the first. When we take that derivative, the derivative of x squared would be 2x. Derivative of 3x is just 3. 2x minus 3, it's the exact same thing, and it better be the same thing because these rules have got to work no matter what. So, absolutely, if you see this sort of problem, every single time I'm going to do what I did over here in blue. That is way easier, a lot less room for error, a lot simpler problem. Can we always do that? Can we always just multiply through? Well, no, because we couldn't multiply an x by an ex. We couldn't simplify that in any way that's going to make our lives easier. So we do have to have this power rule. But sometimes, or we should always be on the lookout for simplification that might make our lives a little bit easier. Let's do another problem. So we haven't done one with the quotient rule yet. Let's do that. So let's take the derivative of 5x over e to the x. So we said with the product rule, it didn't really matter the order as long as we did the derivative of one, left the other, and then reversed it on the second term. With the quotient rule, it does matter the order because remember we have the subtraction in between. We have to do the derivative of the top, leave the bottom, and then we do the derivative of the bottom, leave the top. So I'm going to leave the bottom, which is just e to the x. I'm going to take the derivative of the top, which is 5. I have to subtract from that. This time I'm going to leave the top, which will be 5x. I'm going to take the derivative of the bottom. Well, the derivative of the bottom is just e to the x. And this is over e to the x squared. And that's our derivatives. So we took the derivative of the top, giving us just a 5. We left the bottom exactly as it was. Then we subtracted. We leave the top, and we take the derivative of the bottom, e to the x, just giving us e to the x. Then we have to remember to square out the bottom. I do want to simplify this in any way possible, and I do see an obvious simplification. Every single term has an e to the x, so I can cancel out that e to the x from every term, leaving us 5 minus 5x over e to the x. So it does clean up a little bit, makes it a little bit easier, a little bit prettier. Let's do another one. Let's take 5x minus 3 over 3x to the fourth. I'm going to show you another way to approach this problem in just a few minutes, but if I wanted to use the quotient rule, we can go for it. So the quotient rule says, let's take the derivative of the top, so we have to use a difference rule and a constant multiple rule within this, and a constant rule in fact. But if I take the derivative of the top, that derivative is just going to be 5. Derivative of 5x is just 5, derivative of negative 3 is 0. But then we leave the bottom, and then I have to subtract. Well, now I leave the top, 5x minus 3, and I take the derivative of the bottom. The derivative of the bottom would be 12x to the third. And now I have it over just the bottom, not the derivative, but just the bottom. Move that around a little bit. 3x to the fourth, but I do need to square that. So that is our derivative, but we do want to simplify, so let's work on that next. 5 times 3 is 15, x still to the fourth, minus, well here I have to distribute these terms. So we'd have 5 times 12, which is 60, x to the fourth power. Then there's a negative in front. Then we have a negative 3 will turn into a positive 3, times 12 is 36, x to the third. So we not only have to remember to distribute the 12x to the third, but I'm distributing the negative at the same time. If it helps you to move that around first, you can, doing it all at the same time. Then on the bottom, I have not only an x to the fourth squared, but I also have the 3 squared, which gives me 9. X to the fourth squared will be x to the eighth. Remember, you just multiply those exponents. So there is a little simplification that can take place now. For one, I see like terms. So I can simplify those. That would be negative 45 x to the fourth plus 36 x to the third. And on the bottom, we still have 9x to the eighth. But then I recognize too that I have some things that will cancel. All of these terms are divisible by 9, in fact, 9x to the third. So 45 divided by 9 is 5, and it's still negative. X to the fourth divided by x to the third will be x. 36 divided by 9 is 4. X to the third divided by x to the third is just 1. And then in the bottom, 9 divided by 9 is 1. X to the eighth divided by x to the third is x to the fifth. And that would be our final answer. Now I said there was another way we could have approached this problem and it may have been easier, so let me do that off to the side, do it in blue again. Well, I can always break fractions up into two terms if the denominator is just the one term, right? If these had been switched, I would have had to have used my quotient rule. But because I can break these up into two fractions, I could write this as 5/3 x is in the denominator, or x to the negative 3 in the numerator. So let me make that a little bit more clear. The 5/3 is in front, and x is being raised to the third power, negative 3 power. And then here, negative 3 over negative 3 will just be negative 1, and x will be to the negative 4 there. So then if we apply our difference rule with our constant multiple rule and our power rule, negative 3 multiplied to the 5/3 will be a negative 5. X will be to the negative 4 now. And when we take the derivative of the negative x to the negative 4th, we multiply the negative 4 to the negative 1. That'll give us plus 4. And x will now be to the negative 5th power. Now, if we look at this compared to what we had a second ago, these aren't the same, but they are. So if we want to see how they are the same, I can just break this up into those two fractions. So if I were to take this negative 5x and divide by x to the fifth, that becomes negative 5x to the negative 4, because x over x to the fifth becomes 5 over x to the fourth, comes up to the numerator using the negative exponent. And then 4 over x to the fifth, we can write that as 4 times x to the negative 5. Notice they are, in fact, the same thing. So you get another example where if we had done a little simplification at the start, that is by far a much faster, easier process. So it is always a good idea to look at the problem initially and say, can I simplify this in some way? That's not always possible. Like I said, if we just switch these two things, if I had the 3x to the fourth over the, whatever we had, 5x minus 3, well, now this is not easy to break apart. Could we simplify it? No, we can't, right? We can't break apart that denominator, so we'd have to just take the derivative using the difference rule. All right, sorry, the quotient rule, not the difference rule, but the quotient rule. And we get to an answer. It wouldn't be too bad. It would be the same sort of work we did over here. It's just not a really easy way to do it like what we had done in blue. So this is a good introduction to the basic rules, where you're going to see more rules. You may have heard of the chain rule. That's one that a lot of people have heard of that we haven't gone to yet. But we're going to see other rules for trigonometric functions, inverse trig functions. We're going to have inverse rules, and that'll allow us to come up with the derivative rules for logs and for other exponential functions. So we'll see other rules. These are just getting us to the basics.